Welcome back. Today we're taking another peek beyond the decimal point. If you've ever felt like decimals are just kind of floating arbitrarily in the middle of your math problems, well, you're in exactly the right place. Our goal for this explainer is to build a progressive, totally logical concept map of decimal math. We're going to take those counting numbers and fractions you already know and love and seamlessly expand them into the frankly fascinating world of decimals. Get ready to lock these concepts in, once and for all.
Okay, so here's our roadmap for today. First, the decimal foundation, then rules of decimal multiplication, third, division and place value, fourth, the magic repeating decimals, and finally, number 5, real-world decimal applications.
All right, let's kick things off with section 1, the decimal foundation.
So let's dive right into this. The absolute most important thing to realize here is that decimals, they aren't some weird, isolated set of rules. No, they're simply a natural extension of the Indian place value system that you've literally been using your entire life. Just like we have tens and ones, decimals just continue that exact same logic to the right, giving us tenths, hundredths, and thousands. Take a look at Janelli and Pallabi here. They're playing a pretty straightforward conversion game. Janelli calls out a fraction, and Pallabi fires back with the equivalent decimal. And notice the pattern in Janelli's fractions? 3 over 10, 4 over 100, 67 over 1,000. These specific denominators, your tens, hundredths, thousands, they are the absolute key. When a fraction has a base 10 denominator, it translates perfectly into our decimal system. 3 tenths is, well, simply 0.3. It's a direct one-to-one translation of value. And because of this beautiful base 10 foundation, we get to use an incredibly simple 3-step rule for dividing any number by 10, 100, or 1,000. Let's look at the example of dividing 123 by 10. Step 1, you write your starting number, the dividend, exactly as it is and just pop a decimal point at the very end, so 123.0. Step 2, count the zeros in your divisor. The number 10 has exactly 1 zero, right? Step 3, move that decimal point to the left by that exact count. Move it one spot left and boom, you get 12.3. It works every single time without fail for any base of 10. Moving right along, let's hit section 2, rules of decimal multiplication. Now, at its core, multiplying decimals is still just repeated addition, nothing to be scared of. Let's look at our Shad from our source text. So, he goes to a stationery shop and buys 5 pens. Each pen costs 9.5 rupees, so that's 9 rupees and 50 paisa. To find the total, obviously, we need to multiply 9.5 by 5. But think about what that actually means in the real world. It's really just 9.5 added to itself 5 times, 9.5 plus 9.5, and so on. When you run that addition or perform the multiplication, you get exactly 47.5. Grounding these abstract decimals in a real-world purchase, it just makes the whole operation so much clearer. Now, what's really interesting and honestly kind of counterintuitive about this is the behavior of decimals when we multiply them. I mean, we're all heavily conditioned to believe that multiplication always makes numbers bigger, right? And as you can see in situation 1, if both numbers are greater than 1, like 3.4 times 6.5, the product is indeed larger. It's 22.1. But look closely at situation 2. When you multiply 2 decimals that are both strictly between 0 and 1, let's say 0.25 times 0.8, the product is 0.2. The result is actually smaller than both of the starting numbers. You're essentially taking a fraction of a fraction, which naturally shrinks the final value. Mind-blowing, right?
Okay, let's keep building on this. Section 3, division and place value.
First up, let's just establish our baseline expectation with the quote-unquote normal rule of division using whole counting numbers. Whenever we divide 2 counting numbers, the answer, the quotient, is always less than the starting number, the dividend. For example, you have 128. You divide it into 4 groups, and you get 32. 32 is obviously less than 128. It makes perfect logical sense. You're breaking a large quantity into smaller pieces. Simple enough.
So the absolutely crucial point here is, what happens when we flip the script? What if our divisor is a decimal less than 1? Like, what happens when we divide 128 by 0.4? Well, prepare for the rule of surprise. The answer is 320, proving that the quotient can actually be remarkably larger than the dividend. Think about it this way. You're asking how many 0.4s can fit inside 128. And because 0.4 is so incredibly small, you can fit a whole lot of them inside, 320 to be exact. It completely shatters our standard everyday assumption about division.
All right, get ready for my favorite part. Section 4, the magic repeating decimals.
Let's look at a classic anomaly here. What actually happens when you try to divide 10 by 3 using long division? Well, you start by seeing how many times 3 goes into 10. It goes in 3 times, making 9. You subtract 9 from 10 and you get a remainder of 1. Okay, you bring down a 0, giving you 10 again. 3 goes into 10 3 times, and you get another remainder of 1. You'll very quickly realize that this never seems to end. Because you constantly get that remainder of 1, you are going to generate an endless, infinite string of 3s in the quotient. 3.333, just marching on forever and ever.
But honestly, 10 divided by 3 is just the warm-up. Let's look at dividing 1 by 7. If you execute the long division for 1 divided by 7, you don't just get a single repeating digit. Oh no, you get a mesmerizing cyclical chain of remainders and a quotient that repeats a massive 6-digit sequence. That sequence is 0.142857, and then it repeats 142857, endlessly. The source text actually refers to the specific sequence as a magic number. And it really is. It's just an incredible display of how our place value system handles quantities that refuse to divide cleanly.
Bringing it all back down to earth, here is Section 5, Real-World Decimal Applications. And this brilliantly illustrates exactly why decimals are absolutely critical for our survival on this planet. Literally. I mean, we all say a year is 365 days, but astronomically speaking, the Earth's orbit isn't quite that neat and tidy. It actually takes the Earth 365.2422 days to complete a revolution around the sun. The textbook highlights this under the awesome concept of look before you leap because, well, ignoring that tiny little decimal has massive consequences over time. Let's actually quantify that calendar drift using some decimal multiplication. Every single year, we have 0.2422 days left over. So what happens after 100 calendar years? We just move the decimal 2 spots to the right. Suddenly, we have 24.22 extra days. If we didn't account for those decimal days with leap years, our seasons would completely shift over the centuries. Imagine snow in July. But it's not just planetary orbits, you know. We use these exact same decimal operations to convert 50 grams of spices into 0.05 kilograms at the market, or to calculate precisely how many milliliters of juice each person gets when you split 3 liters equally among 8 friends. Basically, decimals run the real world.
To wrap up our explainer today, I want to leave you with a really fun challenge from history. Sridhar Acharya presents a puzzle from his ancient book, Patiganita. 6 1/4 is divided by 2 1/2, and 60 1/4 is divided by 3 1/2. Tell the quotients separately. So I challenge you to test out your newly minted decimal skills. Can you solve this ancient puzzle? Not by crunching complex fractions, but by converting his fractions directly into decimals first? Give it a try. See how much easier the math actually becomes when you peek beyond the point. Keep learning, keep practicing, and honestly, just enjoy the beautiful structure of the math. See you next time.